Dan is a professor of computer science and electrical engineering at Stanford. He leads the applied cryptographic group and co-directs the computer security lab. His research focuses on applications of cryptography to computer security, and his work includes crypto systems with novel properties, web security, security for mobile devices, and cryptanalysis. So there's no better person to be hearing about this than Dan. He also knows so much about blockchain. He's right now teaching the class about the blockchain and cryptocurrencies. So I'm sure you will learn a lot from him. Without further ado, Dan, you can kick us off.
Awesome. Thank you so much, Petra. So welcome, everyone. Good morning, good evening. Looking forward to telling you about some developments in cryptography the next hour or so, and happy to take questions at the end. And so let's dive right in. So there are actually two topics that I wanted to talk about today. One, as you can see, is on post-quantum secure signatures, and the other one is more applications of zero-knowledge proofs. Okay, so I hope we'll have enough time to go through both of those. But I also want to leave time for questions at the end. So, keep your questions, and we can have a discussion once we go through the material. Okay, so let's get started and dive right in. So, as you know, digital signatures are a pretty important part of cryptography, right? It's a very important primitive. They're used everywhere to authenticate information. They're used in certificates. They are used on the blockchains. They're used very, very widely. So as you know, today we have a number of families of digital signature systems. For example, we have RSA signatures. Those are typically used in web certificates. They're relatively long signatures and long public keys, around 256 bytes signatures. The nice thing about RSA signatures is they're very fast to verify, which is why they're often used in certificates. So certificates are very fast to verify. We also have signatures based on discrete log. These are shorter signatures and shorter public keys. Example schemes are called Schnorr and ECDSA. I'm sure many of you have heard of those. And those are very widely used. In particular, they're very widely used in the blockchain space to authenticate transactions, to do governance, to do consensus, and so on and so forth. And then we have BLS signatures, which are also quite short. And BLS signatures have this remarkable property that they're aggregatable. You can take many BLS signatures and compress them into a short digital signature that's very fast to verify. Yeah, so you can take 1 million BLS signatures and aggregate them into a single signature that's quite easy to verify. They're also very easy to thresholdize, so they're easy to make it so that if you need to support like a 10 out of 20 threshold, it's actually quite easy to do. And as a result of these BLS signatures are used in Ethereum, in particular in Ethereum consensus, and so on. Okay, so those are kind of the classic families of signature systems that we have out there. I'm not going to talk much about these signatures schemes in this talk. I will say that if you want to learn more about them in the winter quarter, where I'm teaching our cryptography class, where we go into infinite depth about all of these systems and explain exactly how they work, how they're used, what's good and what's bad about them. So this is our CS255 cryptography class, which all of you are welcome to take. Now, of course, the problem with these signature schemes is that they are not secure against an adversary that has access to a large-scale quantum computer. So again, I'm sure many of you have heard quantum computers are computers that are based on quantum physics, not classical physics, and in fact, they're able to solve certain problems faster than can be done by a classical computer. Unfortunately, one of the first examples that we have of this is that these quantum computers are able to break all the signature systems that we just described. So the question, of course, you might be wondering, well, how large of a quantum computer do we actually need in order to break these signature systems? So I'll mention that there have been some works trying to estimate the size of these machines and how long it would take. And I wrote some numbers here. These are this is basically citing some recent papers on this. You can see it requires about 20 million qubits and about 8 hours of work to break 24-bit RSA, and similarly for 256-bit elliptic curve cryptography. Yeah, and these are just estimates. Interestingly, there have been lots of recent work on this. Everybody always wants to know, well, when are we actually going to have a quantum computer that's big enough to attack these systems? And the answer is we don't really know. Yeah, so some people estimate decades, some people estimate more, some people estimate less. So we don't really know. What I'll tell you is it's kind of interesting that there's also improvement in algorithms. For example, I'll mention just a very recent improvement that came out this summer due to Regev that basically shows that using a different algorithm, maybe it's possible to factor RSA, the RSA modulus with fewer than 20 million qubits. Yeah, so there's even innovations in terms of algorithms. Okay, so the question is, what do we do about this? And the answer is that we know exactly what to do. Yeah, this is not a problem that we're kind of ignoring. We know exactly what to do. And the answer is we are supposed to be using signature schemes that are resistant to a quantum computer. Yeah, so we're supposed to use these classical signature schemes. So the signature scheme itself runs on a classical computer, not on a quantum computer. But the signature scheme is secure even if the adversary has access to a large-scale quantum computer. That's kind of what we'd like to do. And I'll even tell you that the NSA actually puts out guidance for government contracting, basically for systems that the government buys. And the guidance says that we're supposed to move to post-quantum signature systems, so signatures that are secure against quantum computer. Basically, the transition is supposed to be complete by 2035. That's not a very long time. That's what? That's about 12 years from now. And they put out this long article that explains exactly the reasoning behind this. But the transition is supposed to happen by 2035, at least for securing transactions or for securing information on the web. So this is an interesting timeline that I wanted you to be aware of. Now, before we actually go into the problem that I wanted to talk to you about, I wanted to just mention quickly that, in fact, as many of you probably know, there's a NIST process for standardizing post-quantum cryptography, so cryptography that remains secure against an adversary that has access to a quantum computer. It turned out that actually two of the two of the NIST candidates for standardization turned out to be insecure, in fact, insecure under a classical attack. Yeah, it just shows how difficult it is to design new cryptographic systems. So they went through the entire process, and in fact, it turned out two of the ones that basically survived almost to the very end later turned out to be insecure under a classical attack. So the question is, how do we deploy these new systems in a way that's secure? And so I just wanted to stress that when deploying these systems, it's very important to deploy them in what's called a hybrid deployment, where we use both the pre-quantum system and the post-quantum system. Okay, so in a real-world deployment, what we'll have is the public key will be basically a pre-quantum public key, like maybe a Schnorr or ECDSA, BLS public key, along with the post-quantum public key. And the signature, similarly, would be a pair of signatures, one issued by the pre-quantum public key and one issued by the post-quantum public key. Yeah, and this will ensure basically the fact that we're using both the pre-quantum and the post-quantum public keys together would ensure that even if the post-quantum system turns out to be insecure, we still have the security of the pre-quantum system. And if, in a decade or two or three or four, the adversary builds a quantum computer, then we'll have security based on the post-quantum system. Okay, so I do want you to remember that it's actually quite important to deploy these things in tandem. It's not that we're abandoning the pre-quantum systems. So Schnorr, ECDSA, BLS, all those will continue to be used just in tandem with a post-quantum system. Okay, very good. So, what has NIST standardized? So basically, the NIST standardizing three post-quantum signature systems. Yeah, so they're called the Lithium, Falcon, and Sphinx Plus. Yeah, and I wrote down the parameters for all three, and that's kind of what I wanted to share. So if we look at the first one, which is a pre-quantum system, yeah, here we're interested in the size of the public key plus the size of the signature. Yeah, I don't know if you can see my cursor, but I'm pointing to the first column. So the size of the public key plus the size of the signature. And the second column, the column on the right, basically measures how long it takes to verify each one of these signatures. Yeah, so I'll use DSA or ED-DSA, which is a pre-quantum signature. I'll use that as a baseline for measuring time. So we'll call that 1. Okay, so you can see that for ED-DSA, the size of the public key in the signature is relatively short. It's about 112 bytes. And verification time, as I said, is 1 because that's our normalization factor. Now, when you look at either Lithium and Falcon, these are lattice-based systems. You can see that the public key and signatures are much longer than for ECDSA. They're like almost a factor of 10, order of magnitude longer than for ED-DSA. Verification time is faster, which is cool, but the length is actually a problem. And we'll talk more about that in a minute. The next category are what are called hash-based signatures. Yeah, and hash-based signatures, you can see they perform well. They're only about 1.7 to 2 times slower than regular signatures, The problem with them is that the signatures themselves are actually quite large. Yeah, so it's about 8 kilobytes for Sphinx, and I wrote down 932 for what are called stateful hash-based signatures. And finally, I wanted to mention the last category of post-quantum signatures. These are post-quantum signatures based on what are called isogenies. Again, this is a paper that just came out in 2023. It's called SQI Sign HD, where the signatures are actually not that bad. You know, it's 160 bytes, so getting close to the pre-quantum levels. But of course, verification time is actually quite terrible. You can see it's like 500 times as long to verify these signatures. So these are problematic, but problematic not because of the length, but because of the time. Okay, so this is kind of the state of the art, state of the world when it comes to post-quantum signatures. And what I wanted to tell you is kind of, let's look at the implications of using signatures with these parameters. In particular, I wanted to focus on the length of these signatures that we see here. So the NIST schemes that are to be standardized, you can see they're quite long. And I wanted to talk about kind of the implications of that. Yeah, so you know, as we said here, they're about an order of magnitude longer than what we have with pre-quantum signatures. What that would mean is, like, for example, when you go to a website and you download some web content, the first thing you have to do is you have to download the certificate from that website. But it's not only the certificate from the website you're going to. For example, if you go to the NewYorkTimes.com, they will redirect you to about 20 other websites that serve all sorts of other components of the page, like you know, various ads, various JavaScript components, and so on. So you have to establish about 20 connections when you go to a typical website. And now the certificates for all these websites would be about 10 times longer than they are today. What that means is that the actual messages from the server to the browser that contains those certificates will no longer fit in a single packet. They have to be multiple packets, and that will actually slow things down by quite a bit. So that's the implication for web content. So it can be done, and in fact, there have been experiments that show that it works all right, but it does introduce additional cost. For blockchains, the cost is actually quite more significant. In particular, when you look at transactions, let's just take Bitcoin transactions just as an example. In Bitcoin transactions, most of the data that goes into a transaction actually is the signature data already. Even with short ECDSA signatures, even then, much of the transaction data is the digital signature. If we transition to these post-quantum signatures, now transactions become 10 times bigger, and that's going to increase the size of the chain by a factor of 10. Yeah, so now everybody has to store 10 times more information just because signatures became a lot bigger. So the expense goes up by quite a bit. So so the fact that these signatures are large is problematic for the web, but it's very problematic in the blockchain space. And so the question is, what do we do? Whoops, I skipped on something. So the question is, what do we do? I should say, so because of this, actually, NIST actually reopened the call for proposals. They actually asked for additional post-quantum signatures by the summer, and there's additional review for post-quantum signatures that's going on right now. Okay, I guess before we talk about what can be done about better post-quantum signatures, one thing that I wanted to mention is that one area of computing that's kind of important to move to post-quantum signatures is what we call signing software updates, right? So the situation is this: imagine somehow tomorrow morning you wake up, you open the newspaper, and you read that actually somebody built a quantum computer that's able to break one of these existing signature schemes. Well, that would mean that now an attacker can sign rogue software updates and distribute them to the entire world, and they would look perfectly fine for every client's computer out there. And so these rogue software updates would be installed everywhere. So this is kind of this is kind of a critical resource. Basically, signing software updates is something that we have to make sure is secure. And so one would like to use actually the most reliable signature schemes that we have for that application. And what's interesting is that for that application, because you're downloading a relatively large software updates, it's tens of megabytes. It doesn't really matter if the signature scheme is 100 bytes or 10 kilobytes. It's still negligible compared to the actual software update that you're downloading. So we'd like to use super secure signature schemes where the size of the signature doesn't really matter. And for that, it actually makes a lot of sense to use what are called hash-based signatures. Yeah, so this is a bit of a call to arms. So I hope some of you actually have a say in how industry actually signs software updates. And I think it's actually quite important in the short term to move from the existing digital signature schemes that are being used for software updates to these hash-based signatures. Yeah, there are, as far as we can tell, these are the strongest signature schemes that we have. They're a little bit long, but it doesn't matter in this context. And so this is actually quite important to transition to. So hopefully we can convince, with your help, we can convince industry to actually do this move to hash-based signatures, at least for software updates. All right, so and this is something that would be great to discuss more in the Q&A session to see basically how can we actually speed this along. All right, so that's kind of the situation with with hash-based signatures and software updates. So next, I wanted to talk about basically, other types of other ways to build short and efficient post-quantum signatures. Yeah, so this is kind of the open problem that I wanted to tell you about. Basically, how do we build short and efficient post-quantum signatures? Today, the answer is we don't know how to do it. Yeah, either we have long post-quantum signatures that are efficient, or we have short post-quantum signatures that are inefficient. And the question is, can we have the best of both worlds? All right, and so what can we say about that? So there was a promising path that for a while I was actually quite excited about, and we spent quite a bit of time trying to use it, and that's using what's called cryptographic group actions. Okay, so let me tell you what a cryptographic group action is, and then we'll see whether that can actually lead to short signatures or not. So, okay, so here we have to do a little bit of math. So let me explain what a group action is. So let's say we have a finite group denoted by G. Yeah, so we can multiply elements in this group and get, we can multiply two elements in this group and get a third element. And this group is actually acting on a finite set X. So what does it mean for a group to be acting on a set? Well, what it means is there's an operation. It's a binary operation called a group action, denoted by star. And you see this group action takes a group element and an element from the finite set, and it outputs an element from the finite set. So the group, a group element acts on an element in the finite set, and it outputs another element in the finite set. Now, of course, it has to satisfy some properties. And so the properties are basically that the group action is compatible with the group operation. What does that mean? That means that if I take a set element X and I act on it with a group element G2, and then I act on that with the group element G1, that's the same thing as acting on the set element X using the product of G1 and G2. Okay, so in some sense, kind of this is the compatibility property that the group action basically is compatible with the actual group operation on the group itself. Okay, so that's one property, and the other property is, of course, if I act on an element X with the identity element of the group, I should get the element X. Okay, so that's called a group action. Yeah, and there are many group actions. Actually, mathematics is littered with group actions. They're like everywhere. There are lots of groups that act on sets. So the question is, how is this useful for cryptography? Well, so we have to define, first of all, a hard problem. And it turns out the hard problem is very similar to what's called a discrete log problem. So let me explain what the hard problem is. On group actions, so this is called the group action discrete log problem, which is the following. Basically, I give you two elements in a set, x1 and x2, yeah? And your job is to find an element G in the group such that if I act on x1 using G, I get x2. Okay, so basically acting on x1 using the group element G maps us to x2. We call this the discrete log problem. It's a very different discrete log problem than what we're used to for building digital signature schemes, because now we're dealing with group actions, but it has kind of a similar flavor if you think about this to traditional discrete log. Yeah, so we say that if the discrete log problem is hard, then we say that star is a cryptographic group action. Yeah, if this problem that we just defined cannot be solved by an efficient algorithm, then we'll say that star is a cryptographic group action. And it turns out we actually have lots of examples of cryptographic group actions. This captures things like isogeny group actions, and there are many other examples in mathematics. Yeah, so we have a whole bunch of candidates for these cryptographic group actions. Okay, so why is this interesting? The reason this is interesting is that this discrete log problem seems to be much more resistant to quantum attacks. Yeah, in fact, you might know that the quantum algorithm that breaks the traditional signature schemes is due to Shor. It's called Shor's algorithm. It turns out Shor's algorithm actually doesn't work when the set X is not a group. Yeah, if the set X is just a set, but is not actually a group, then there is no, Shor's algorithm does not attack these systems. The best known algorithm for attacking such systems is, it's a sub-exponential attack due to Kuperberg, but the fast attack that we know of actually does not apply to these group actions. Great. So the question is, can we use them to build short digital signatures? Yeah. So can we use these schemes to build digital signatures? And the answer is yes. There are actually lots of constructions that use group actions to build short signatures. One example that's actually very elegant is called cSign. Here I linked to the paper here. It's a paper from 2019. And it turns out the public key plus signature size is about 3 kilobytes long. Yeah, so still quite large. Remember, we wanted something that's about 100 bytes long, and this is 3 kilobytes. So for a long time, we were wondering, can we do better, right? So, EDDSA is like 0.1 kilobytes, like 100 bytes. And here we're stuck with 3 kilobytes. So the question is, using group actions, can we do something that's actually better than cSign and actually maybe as short as EDDSA and maybe hopefully as efficient? Well, unfortunately, like in a recent work, we showed that this is probably not going to work. So for a long time, we tried to do it, and then when we saw that we couldn't, we asked, well, maybe there's some sort of a fundamental block that prevents us from doing it, and the answer is yes, there's something that prevents us from doing this. So this is joint work with Guan and Zandri. It appeared earlier this year. So what we show is basically here. What we show is basically that all these discrete log signatures, they come from what are called identification protocols. Yeah, we take an identification protocol and we make it non-interactive. And what we show is, if you look at an identification protocol in this, what's called a black box group action model, that's kind of a abstract group action model, then it must be that the amount of information that's being exchanged is roughly lambda times log lambda. Okay? Lambda times log lambda. Well, because the set X has to be at least size 2 to the lambda, what that means, so we have to send lambda log lambda elements in X. Each element in X must be at least lambda bits, which means that the resulting signatures have to be of size lambda squared over log lambda. Yeah. So they have to be, unfortunately, what this means is signature size has to be roughly lambda squared. So it's quadratic in the security parameter. Yeah. And if a signature is going to be quadratic in the security parameter, in practice, that means the signature has to be over 2 kilobytes. Yeah. So that's kind of the bad news. That we were able to prove that we're not going to achieve 100 byte signature schemes here because effectively signatures have to be quadratic in the security parameter. So this is a little bit of bad news, but it's good to know. Even if something is not going to work, it's good to know that it's not going to work. Okay, great. So that's kind of where we are. And so the current state of affairs is that we're actually still looking for short and efficient post-quantum signature schemes. And I would kind of ask for your help with this. This is, I think, one of my favorite open problems. Like, I would really encourage people to think about this. It's probably going to take some dramatically new idea. So some new scheme that is going to be believed to be secure against a quantum computer, and it needs to be as short as, say, ECDSA, and as efficient to verify. Yeah, still an open problem, and would be wonderful if actually one of you can solve it. I think this is actually quite important. It's actually really kind of holding back the deployment of these signatures, both on the web and in the blockchain space. So this is a pretty important problem to solve. Hopefully, we'll see progress on this in the next couple of years. All right, so this is kind of the first topic I wanted to tell you about. The second topic I wanted to tell you about is it has to do more with zero knowledge, which is what we promised in the title of this session. And so let's talk about using zero knowledge to prove content authenticity. Okay, so this is a very cute, I think it's a very cute application of zero knowledge proofs to actually fighting disinformation. Okay, so let's see how this works, and then I'll open it up for questions. So this is kind of a fun application of zero knowledge. I guess the first thing I have to do is explain to you what is a zero knowledge proof, or more precisely, what is for us, what is a snark? Yeah. So a snark is kind of this amazing primitive. It's really quite a remarkable thing that's gotten very practical in the last decade. And so let's describe, first of all, what is a snark, and then we'll see the application. So a snark is basically a very short proof, succinct proof that a certain statement is true. For example, maybe I want to prove to you that I know a message M such that SHA of M is equal to 0. Yeah, so SHA-256 is a classic hash function. And I want to prove to you that I know a message M such that if you hash M using SHA-256, you get 0. Now, a snark would do this in a remarkable way. It will produce a proof that's very short and that's very fast to verify. Now, the important thing to stress is imagine the message that I know is a gigabyte long. Yeah. The trivial way to prove to you that I know this message is I could just send you the message and you can verify for yourself that SHA of M is equal to 0. But you realize that proof is not short. It's a gigabyte of data. And second of all, verifying the proof is a lot of work. You have to hash a gigabyte of data now and test whether the result is 0. Yeah, what a snark allows you to do is prove that the hash of a gigabyte is 0 using a really short proof. The proof is about a kilobyte, no matter how long the message is. And it's also really fast to verify. It's like 2 or 3 milliseconds, no matter how long the message is. Yeah, so it's kind of remarkable that snarks let you prove these really big statements with very short proofs that are fast to verify. Now, we can extend the notion of a snark using what's called a ZK snark. We can add zero knowledge to the property and require that actually the proof that I know such a message reveals nothing about the message M. By the way, I'll say that the hard part is constructing a snark. Making it zero knowledge usually is actually pretty easy. Usually it's actually just a couple more steps and the snarks become zero knowledge. Okay, so that's what a snark is. There's actually a lot of commercial interest in snarks today. I listed some of the companies that are working in the snark space. It's really quite remarkable. These are large, well-funded companies that are all building and deploying snarks. Let's see, the top line consists of companies that are using snarks. The second line is examples of companies that are actually building snark systems, so libraries. And the third line are companies that are building hardware to accelerate snarks. So it's really quite a large ecosystem, and it's kind of remarkable how much commercial interest there is in building these snark systems. Yeah, and there are actually lots more other companies that are making use of this stuff. So why is there so much interest in this now? Like, what happened all of a sudden that all these companies popped up? Well, really, what happened is that there's kind of a breakthrough in the last decade. There's been kind of a breakthrough in these snark constructions, and that finally we have snark systems where the provers are really fast. Yeah, so I can give you this gigabyte message, and I can construct a proof that I know such a gigabyte message, and I can do it relatively quickly. Yeah, this required a whole bunch of beautiful ideas. Yeah, really, really, really beautiful ideas. If you want to learn more about that, I can tell you that, for example, we have a class on blockchains that I teach. Like, I'm teaching it right now, but I teach it every fall. And a big chunk of the class is devoted to how snarks are actually used in blockchains and how they work. This is CS251. You're welcome to join the class. All the material is available online. You can also look up the material on the course website and see exactly what's covered. So this is one way to learn more about this topic. And again, what I said, that the breakthrough is that generating a proof generation time is about linear in the size of the computation. Yeah, so effectively, it takes only a constant factor more than actually doing the computation. It allows you to actually compute the proof as well. Yeah, so the constant is not a small constant, but the fact that it's a constant is actually already very, very exciting. Okay, great. This is a super active research area. It's a lot of fun to work in this space. Lots of beautiful ideas coming up all the time. It's really quite an active area. I guess I mentioned some of our works in the area, but it's really, I have to say, it's a lot of fun to work in the space. And if you like mathematics, and particularly working with polynomials, it's a lot of polynomial algebra, very, very beautiful ideas about polynomials. If you like algebra and you like to see real world applications of that work, this is a kind of a fantastic area to work in. Okay, good. So what I wanted to tell you about is a cute application of these snarks for content authenticity. Yeah, this is something that we presented. This is joint work with one of my students. Trisha Data was presented at Real World Crypto in Japan earlier this year. Yeah, so let me tell you the problem. The problem is that there's a lot of disinformation out there, in particularly when it comes to images and video. Yeah. So in particular, there's lots of, this is such a problem that, news organizations constantly put up news reports about this. Like here, for example, is a report from the BBC that says there are many misleading images about the conflict in Ukraine. somebody posts an article with an image claiming to be from Ukraine, but then it turns out to be from somewhere completely different at a completely different time. Yeah, and this is such a problem that you'll find many articles about all this, these issues that people post images, people write articles and include images that are simply taken at a different time in a different location. So the industry is kind of aware of this problem, and to solve it, the industry proposed the standard. It's called the C2PA standard: content, provenance, and authenticity. C2PA. And what it does is introduces a technical way in which you can verify when a picture was taken and where it was taken. And this was actually released last summer in a camera, in a Sony camera, that basically includes a C2PA component. So this Sony camera effectively has a signature key embedded in it. Yeah, so you can sign images from the camera. So as you take a picture with this camera, the camera will go ahead and sign those images. And the point is that you can see that basically the camera adds a signature, the C2PA signature, that signs the image along with the location and the time when the image was taken. And again, the point is, if you embed this in an article, the browser can go ahead and check that the metadata of the image is properly signed so that the image really was taken at the time and place that the article is claiming it was where it was. Yeah, so this is basically what C2PA is about. It's about how to authenticate the origin of images. Okay, so this makes sense, I hope. Yeah, this is kind of a very natural application of digital signatures. Very cute. And if you think about this a little bit, you see that there are actually some security issues around this. For example, what happens if somebody is able to extract a secret key from the digital camera and so on. But in fact, there's a paper exploring the security of C2PA. But for now, for this talk, I'm going to ignore all that because I want to show you the application of zero-knowledge techniques. So where does zero-knowledge come in? The problem is that this is actually not how the world works. Yeah, so in practice, when newspapers get a photograph from a photographer, the photographs typically are processed in some way. So for example, this Sony camera that I told you about, it generates pictures that are about 30 megapixels, so 30 million pixels. It's a very, very high definition camera. What the newspaper will do is it doesn't want to send such a high definition picture to its readers. So the first thing it will do is it will resize the image to about 1500 by 1000. Yeah, so resizes the image to much, much lower resolution so that the bandwidth, so to save bandwidth. Then it will go, sometimes it will go ahead and crop the image. Sometimes it will turn it into grayscale and so on. And in fact, the Associated Press has a list of like 6 operations that the newspapers are allowed to do to images like resizing, cropping, and grayscale. The problem now is that once you do this, when you send the processed photo to the laptop can no longer verify the signature, right? To verify a signature, you need to have the original image because the signature was on the original image. So now, by doing this post-processing, the laptop can no longer verify the embedded signature. And so the question is what to do. And that's where zero-knowledge comes in. Yeah, so here's a cute proof using a zero-knowledge proof. And so cute application of zero-knowledge proofs. And so the idea is that if instead of embedding a signature in the processed photo, we're going to embed a proof in the processed photo. And now what are we proving? The statement that we're proving is, the newspaper is proving, the laptop actually receives the edited image and the operations that were applied to the image. And what the newspaper is proving is I know an original image and I know a signature, right? That's what the newspaper is proving, such that the signature is a valid C2PA signature on the original image. The edited image is the result of applying, cropping and rescaling to the original image. And the metadata in the edited image is the same as the metadata in the original image. Okay, so those are the 3 statements that the SNARK proof is proving. And now the laptop will just verify this proof. And if the proof is valid, it will show the metadata to the user so the user can verify where and when the image was taken. Okay, so I hope this is clear. Yeah, so the SNARK statement here is very specific, right? The laptop has the edited image in these operations. And the SNARK proof is basically proving these 3 statements here that I just wrote here. Okay, so that's the idea. And it turns out this works out really quite well. Yeah, the proof size is succinct. It turns out it's less than a kilobyte. Yeah, so it's quite easy to attach this to the edited image. Verifying these proofs is quite easy in the browser. It takes about 2 milliseconds. Yeah, so you can just verify, the browser can easily verify that the proof is generated. correctly, the proof is valid. And the question is, how long does it take to generate such a proof? Yeah, so the newspaper has to do these proofs, one proof per image. So again, it turns out that these images are actually quite large. They're like 6,000 by 4,000 pixels. And you want to resize, crop, and maybe grayscale them. It turns out that with enough hardware, you can actually generate these proofs in just a couple of minutes. Yeah, so if the article contains like 1 or 2 images, it would take the newspapers a few minutes of processing, and it can generate the proofs, and then it can send those proofs to everybody in the world, to every customer in the world, every client in the world, and every client will verify the proof. Yeah, so that's kind of the idea behind this. It's kind of a cute application of snarks, of particular ZK snarks, that allows you to prove that you know a signature on a processed image. Okay, so I should mention, people also wanted to apply this to videos, and so actually now we're working on generalizing this beyond images to videos. But I'll tell you that even for images, this was actually quite difficult, in that the image size, as I said, is quite large. These are 30 million pixel images. Each pixel is about 3 bytes, right? For red, RGB, red, green, blue. So each pixel is about 3 bytes, and so these images are about 120 megabytes. And so when you need to generate this signature, when you need to generate this proof, the first thing you have to do is prove that you have a valid signature on the original image. So it turns out to do that, you have to hash the original image, and hashing 120 megabytes inside of a zero-knowledge proof turns out to be quite difficult. Yeah, this takes actually too long to do using SHA-256. This wouldn't work if we had to hash 120 megabytes inside of a zero-knowledge proof. And so what we did is we kind of developed a new way to do this. We use what are called lattice hashes, which are very efficient and very friendly to zero-knowledge proofs. These lattice hashes will hash the 120 megabytes to about 32 kilobytes. Yeah, so they compress by quite a lot, and they do that quite efficiently. And then finally, we take the 32 kilobytes and compress that down to 256 bits using a hash function called Poseidon. Yeah, and so it's kind of a 2-level hashing scheme, and that's what made it possible to get this system to work, so that the proven time is reasonable. All right, so I just kind of wanted to show you kind of one idea that it took to make this work. For videos, the problem is much harder because videos are not measured in hundreds of megabytes, they're measured in gigabytes, and so the problem is actually even more difficult, and actually that's something that we're working on right now. Okay, so I think this brings us to the end of this talk. So I'll say that this is an amazing time to be working in cryptography. So many new ideas coming up with these snarks, with these post-quantum systems. There's lots of open problems to work on, lots of ideas to explore. So we're having a blast. It's a really fun area, and I encourage all of you to kind of learn more about cryptography. And as I said, if you want to learn more, there's a bunch of courses that I and we teach, so you're welcome to take any of those. As I said, even in the area of snarks, there's a lot more to work on. For example, building faster provers with lower memory footprints. We'd like to get shorter proofs. We'd like to make them quantum resistant. We'd like to get rid of trusted setup. We'd like to have to be able to do proofs on what are called distributed witnesses, when the witness is distributed across multiple parties, and so on. So there's still lots and lots of work to do on these snarks. And that's kind of working under the hood in designing snarks. And then there's a lot more work to do in designing new applications for snarks and for ZK snarks. And that we see a lot in the blockchain space, lots of new applications for snarks. And actually what we're looking for is kind of more applications for snarks, even outside of the blockchain space. Yeah, the example I showed you here for image authenticity is an example of an application outside of the blockchain space. And it would be wonderful to see more examples like that. So I encourage you to kind of look for more applications, and those are always very welcome and exciting to kind of read about. Okay, so I hope this was clear. Hopefully I didn't go too fast. And so I think I will stop here, and yeah, happy to take any questions if there are any. So thank you all very much.
Great, thank you so much, Dan. And so much is going on. Like your lab must be super busy at this time with doing all this work. We got a lot of questions. We will try to get to as many as we can. We probably won't get to all of you, but we will try to get as many as we can. So maybe, Dan, the first questions were more about kind of the post-quantum cryptography and about the timelines. And people are asking about kind of your idea on like when we will get quantum computer, and also like how does it align with trying to solve all of these questions, and why it's important to work on them right now if we are kind of still a little bit ahead.
Oh yeah, for sure, yeah. So I guess the first question which everybody asks is, when are we going to have large enough quantum computers that will actually threaten the crypto that we have today? You know, the answer is that we really don't know, right? You will get different answers from different people. One thing I can say is, up until these recent algorithmic improvements, the number of qubits looked like we would need around 10 to 20 million qubits to carry out the computation. And so just trying to use Moore's law to estimate how long would it take to get to 10 to 20 million qubits. Today we're at around 100 or 200. So assuming doubling every 18 months, you get about 20 to 25 years or so. So that's one way to do the estimates. But then the algorithms are getting better, so maybe fewer qubits are needed, and maybe there'll be improvements that speed things up faster than Moore's law. So the answer is we don't really know. Yeah, we just don't know. And so the question is, what should we be doing today? And here I have to separate this question for the difference between encryption and signatures. For encryption, things that you encrypt today, you would like them to be secure for like 50 years. Yes, so even if somebody records your ciphertext today, you'd like that in 50 years, they would still not be able to decrypt them. Well, if somebody records your ciphertext today and in 50 years they have a quantum computer, then of course they'll be able to decrypt. Yeah. And so things that we're encrypting today might become insecure once we have quantum computers. And so for the purpose of encryption, it's actually kind of important to try and move to post-quantum encryption as quickly as possible so that we maintain confidentiality forever. So that's in the area of encryption. In the area of signatures, or more generally, content authenticity, there we have a bit more time. Yeah. So there, in some sense, once we know that quantum computers are coming, so maybe a few years before, as they start to scale, and a few years before they become large enough, you can imagine transitioning to these new systems, and and security will be restored. As I mentioned, the timeline for NSA is 2035, so they're actually quite aggressive in trying to get people to move. So that's their recommendation, and I see no reason not to abide by what they're saying. Yeah, and so lots of activity. As I said, we still need better post-quantum secure signatures. We need short and fast post-quantum secure signatures. This is stuff that I'm super interested in. I hope you guys would be interested in working on that. And so more ideas are needed. Yeah, so maybe I'll leave it at that. It's a great question. Thank you.
And that was actually another question about, how to develop these or how to accelerate it. So like, how can people on this call kind of try to think about this idea? Are there some approaches that you find as like especially promising, like what they could be thinking about, like how to accelerate this? And just to clarify, the creation of hash-based signatures for signing software updates.
Yeah. So right now we have these three categories, right? We have these hash-based signatures, we have lattice coding-based signatures, and we have isogeny or group action-based signatures. I think it'd be great to find more. Why are we stuck with those three, right? It'd be great to find more categories of signatures. So, I would encourage you to think broadly. Like maybe there are other problems that are hard for a quantum computer that we can then use to build cryptography off of. Yeah, it reminds me that there's a really wonderful website. It's called the Quantum Algorithm Zoo. You can go check it out. It's a kind of a fun website. It shows all the algorithms that we know, all the quantum algorithms that we have for various problems. And then there's lots of open problems, right? Problems for which we don't have quantum algorithms. And so maybe one of those problems for which we don't have a good quantum algorithm, maybe one of those problems we can use to build these good digital signatures. So in cryptography, we like hard problems, right? We like problems that we don't know how to solve because we can use them to build crypto systems. So maybe go out, look for problems that are hard to solve on a quantum computer, at least problems that we don't have good algorithms for, and then try to see whether we can use them to build these short and efficient signatures. That would be one way to go about this, which would be really exciting. So looking forward to what you find out, what you discover.
A follow-up question. It seems that a lot of the solutions are kind of like software-based. Is there any kind of hardware-based solution, or like, are there some ways of thinking about it from kind of the hardware perspective?
You mean for, this is with respect to the first part of the talk or the second?
For encryption and for the first part of the talk.
Oh, I see. I see. Yeah, look, I mean, hardware-based systems are, you know, so I guess this would go under the name of hardware enclaves. Yeah, so those are used for more sophisticated operations, right? So for what we discussed, just digital signatures, no, you have to. These would be pure software solutions. If you need to do more complicated things like computing unencrypted data, then you know, there are, maybe this is when you would start looking at hardware enclaves and what can be done with hardware. But yeah, right now, for digital signatures, we are primarily interested in software-based solutions. Yeah, so we're interested in algorithms, not hardware. Yeah, it's a good question.
Great, thank you. You covered a lot of topics in the modern kind of cryptography. Like, what are you the most excited about? Like, if you had to pick one to kind of spend your next 5 years on, like, what would it be?
Well, look, I mean, there is a lot going on in the world of cryptography. Yeah, so I personally really like the area of snarks just because there's so much activity and there's so much to do. But there's lots of other things going on in the world of cryptography. Maybe I'll mention one thing that's really exciting, which is fully homomorphic encryption. Yeah, computing on encrypted data. That's like something that we covered, I think, in an earlier webinar. Yeah, so there's a lot of commercial interest in this. There's a wonderful company called Zama that's trying to commercialize fully homomorphic encryption, FHE. One of their cool applications is, for example, running machine learning algorithms on encrypted data. It's kind of amazing, right? This is stuff that it sounds like science fiction. I can give you an encrypted image, and you run a machine learning algorithm on the encrypted image, and you get an encrypted classification, which you send back to me, and I can decrypt. Yeah, and now learn the classification. So I basically got you to run your secret model on my secret data. I get the answer, and you learn nothing about my image. It sounds amazing. It sounds like this is like stuff that we couldn't do before, and now we can do it with very little communication using these tools from Zama. So that FHE is a very exciting area in cryptography. I'll mention another area which is called ORAM, which is basically stands for oblivious RAM. You know, how do we read data from a database without revealing the access pattern to the database? So without revealing to the database or revealing to memory what elements in the memory we actually touched. Yeah, and so there's a lot of activity in the oblivious RAM space. There's applications for it in the blockchain area, for privacy applications and so on. So yeah, you know, what can I tell you? And I can go on and on and on. There's like so many new developments in cryptography. Maybe I'll mention one more result, which I really love. This is a paper from Henry Corrigan Gibbs and his group in the last year. It's called Tiptoe, which is basically showing how to run a search, like Google search, on encrypted queries. Yeah, so I can send an encrypted query to Google. They can run a search on this encrypted query, send me back the encrypted results, and I get the results in the clear, and they learn nothing about my query. It's, again, things that we thought are not possible are all of a sudden becoming possible thanks to these new ideas. So this is like a really fun time in cryptography. There's like endless new problems to work on, and that's a really exciting field.
Great, thank you. There were also follow-up questions about kind of post-quantum signatures and blockchain, and like how blockchain kind of it intervenes with this whole thing. So like, could you tell us a little bit more about it? There were a bunch of questions kind of related to different aspects of that.
Oh, yeah. So yeah, this is, I guess this question is basically, how would the blockchain transition to the world of post-quantum signatures? Yeah, and I have to say that that is easily an hour-long presentation. Yeah, it's a fairly detailed topic. Maybe to keep it, just to keep it short, I'll say that, you know, today, if you hold, let's say you hold funds in Ethereum, yeah? So today in Ethereum, you know, you sign using whatever, traditional Ethereum signatures, for example, would be some discrete log-based signature scheme. If you see that, you know, in 2, 3, 4, 5 years, you suspect that a large enough quantum computer will be available, you know, maybe, you know, in 20 years, you start to get nervous about these quantum computers. what you would like to do then is generate a new public key for yourself that is post-quantum secure, and then transition all your funds from the pre-quantum address to the post-quantum address, right? That would be a transaction that you deploy and just move the funds, so now the funds are secured using a post-quantum signature scheme. What's interesting is in Ethereum, with the deployment of account abstraction, you can actually specify whichever signature scheme you want in the account abstractions paradigm, right? And so transitioning your address from a pre-quantum to a post-quantum signature actually doesn't require any changes to Ethereum. You can just implement that using account abstraction, and that would work quite well. So it would require everyone to actively move their funds, but that's not out of the question, and people are of course incentivized to do that. And so that's one way to do it. I can say that there's lots of other ideas for how to do the transition. In fact, you can generate public keys today that are future-proof, that will be secure against the quantum computer later on, but maybe this is taking us a bit too far afield. So why don't I leave it? I'll leave it at that, and it's a good idea for a future webinar. Maybe we can talk about how blockchains can transition to post-quantum signatures. It's a very good question.
It sounds great. Let's do that. Couple more questions, and I think we will be wrapping up afterwards. So one of them is about zero-knowledge proofs and how they are enhancing security and privacy in digital interactions. And also, are there any other privacy-preserving technologies outside of the zero-knowledge proofs?
Oh my God, yes, there are many privacy technologies. Yeah, let's start with the first part of the question. So you're asking, how do zero-knowledge proofs help with providing privacy? Yeah. So I'll give an example in the blockchain space, which is kind of the classic example, which is if you want. So let's see. So today with blockchains, of course, blockchains are transparent, which means that all transactions are available in the clear. Yeah. So if you can look at the blockchain and see exactly who is transacting with who, exactly what's running, and so on. Now that has a lot of benefits, but it also has some drawbacks. So just to give an example, like if a company wants to pay their employees using cryptocurrency, those would be transactions that are recorded on the blockchain, and the whole world will be able to see those transactions. So really, if a company pays its employees using a cryptocurrency, everybody will know what the employees' salaries are, which is a bit of a problem because it means that basically companies cannot use cryptocurrencies to pay salaries. Similarly, in supply chains, if company A pays company B using a cryptocurrency, everybody will know how much exactly the companies are paying one another. And that's something that often companies don't want to support, don't want to reveal. And so there is definitely a need for blockchains that provide some privacy. Yeah, so the whole world can't see all the transactions. But then if you have a private blockchain, by the way, a private blockchain doesn't mean absolute privacy. You could still have privacy, for example, from the whole world, but not from the operator of an operator or so. So there are many different levels of privacy. And so if you do have a private blockchain, the question is, how do we verify that all the transactions on the chain are valid? If I can't see the transactions, how do I know that the chain is operating correctly? And that's where zero-knowledge proofs come in, right? So what we can do is we can post encrypted transactions to the chain, and then next to every encrypted transaction, we write a zero-knowledge proof saying that the transaction is valid. So no money was created, no money was lost, the transaction was properly authorized by the sender, the transaction was properly received by the recipient, and so on and so forth, right? So zero-knowledge proofs can allow us to do what we call a private transactions on top of a public blockchain. Everyone can verify that the chain is progressing correctly, but the transaction data itself is hidden. Now, interestingly, by the way, there are lots of proposals for how to reconcile this with regulatory compliance. In the US, there are many regulatory requirements on all transactions. And so it's very interesting that the zero-knowledge proof can also provide a proof that regulations were met. For example, if there's some reporting requirements, a zero-knowledge proof can prove that the reporting requirements were met, and so on. So it's even a way, these zero-knowledge proofs are even a way to build compliant private blockchains. Yeah, so they're going to play quite an important role. Again, if businesses are going to use these blockchains, there has to be some level of privacy provided. And the easiest way to do that is, privacy with compliance. And the easiest way to do that is through the use of these zero-knowledge proofs. This is why there's so much demand and emphasis for this field, and that's why it's progressed so much in the last decade. Yeah, again, it's a very good, very big topic, and a very good question.
Perfect. Thank you, Dan. Just to wrap us up, as always, people are asking for additional resources, like how to learn more, any book recommendations, any blog posts, any podcast, anything you have, like you could share. They are interested to know.
Oh, yeah. You know, that's a great point, actually. I guess maybe I'll add the slides to the end of this presentation with a bunch of, where to learn more. I should have done that. So I guess when we post the slides, we'll include a link to more resources. I'll say if you are eager to get started, one place to start is you could just go to my blockchain class, cs251.stanford.edu. All the material is available online, and in the lectures there are lots of links to supplementary material. So if you look at the syllabus, you'll find lots of links to supplementary material, and that maybe is a good way to start. But I'll also post more resources in the slides. If you want to learn more about cryptography, well, what can I say? I'll shamelessly plug my own book. If you go to cryptobook.us, this is a book about cryptography. It's a graduate book in applied cryptography. It's freely available. You can download the PDF, and please send me any comments. I take all the comments very seriously and address all of them. So you're also very, very. That's another great way to learn about what's happening in the world of cryptography.
Perfect. Thank you, Dan. And I posted these in the chat, so hopefully on your platform these should show up. Thank you so much, Dan, for taking the time for this webinar. Thank you, everybody who had a chance to join us. I hope you had a great start of the week. That's the wrap. Thank you.
Yeah, thank you all. This was a lot of fun, and have a good week.